So if a small piece of rock has a gazillion atoms and it goes into space, so just a rock goes into space, do the number of atoms change? No. Does the mass, remember that's a gazillion atoms, does the mass of those, since the number of atoms doesn't change, does the mass change between the Earth and the moon? No. Does the weight change? Yes, because the gravity that's pulling on it changes. You'll have Earth's gravity and eventually you'll have moon's gravity. So mass is what we use every day when we're talking about scales. Weight is actually a crazy unit. It's a Newton, and it has to do with gravity pulling on you. And let's look at conservation of matter. So conservation of matter says there's no change in the number of atoms in a phase change. So that's when you go from like a liquid to a gas or a solid to a gas. You don't change the number of atoms there or in a chemical reaction. So the idea is that if you start with a certain number of atoms on one side of a reaction, you don't just have some of those atoms blip out into nothingness and then have 3 at the end. You still have them. It's just that maybe these 2 here that were stuck together, or these 3 that were stuck in a clump of 3, maybe one of them breaks off and sticks to the other 2 atoms. You still have 5 atoms. They just rearrange themselves. They don't blip away and disappear. And even when you're boiling liquids, however many atoms that you have in your liquid, and obviously there's so many more than 4 that I'm drawing, but when you boil those atoms, it might appear as though you've lost them, but they haven't blipped out. They just happen to be in the air around the flask. They're not gone from existence. They just are in the gaseous phase and they're in the air around it. So that's the law of conservation of matter. And there's a related law, conservation of mass, that comes in chapter 2. So think about these questions and see if you can answer them.